I told Colin I would post some information about how to zero a rifle, or you can say, most people do zero a scope or sight in the rifle. What that means is when you put a scope on a rifle, a telescopic sight, it means to align or adjust the scope so that when you aim it, get its crosshairs, its reticle on your target, that will be the point of impact of the bullet. How to accomplish that practically can be explained in probably 2 minutes, but when I learn something new, I enjoy learning the theory behind it, a little bit about why it works. So I'm going to explain some of those things. I got started on this project and wound up with a 30-minute video and still hadn't finished. So I'm going to instead present the information in a series of shorter posts, some videos, maybe some text and still pictures. Anyway, here goes the introduction, and for a lot of you this will be old hat, ho-hum, stuff you already know. For those of you who are not familiar with rifles and scopes, I think it might be helpful and interesting. So anyway, I'll be quiet and we'll get on with it. If I release a rock from my hand, the force of gravity pulls it down to the ground. And even if I throw the rock outward, as it is flying outward, it is also being pulled down by gravity toward the ground. Likewise, if I drop a bullet from my hand, if I release one, it will be pulled to the ground by gravity. And even if I shoot the bullet outward from a gun, as it is flying outward, it will simultaneously be pulled by the force of gravity toward the ground. A simple quadratic equation describes how far in feet a released object will fall due to the force of gravity in some given time t in this formula, expressed in seconds. D equals 16 t squared. Here's a simple example. If an object is released and falls for 2 seconds, the distance it falls, d, will be 16 times 2 squared. That's 16 times 4. So it will fall 64 feet in those 2 seconds. We're now going to spend some time looking at this diagram. Look, please, at the dark line angled upward a bit on the diagram on the lower left side. That represents the barrel of a rifle. Above it, the narrow rectangle represents the lens assembly inside the scope, inside the telescopic sight, which we commonly call the scope on the rifle. And I label it lens assembly inside the scope for a particular technical reason that we'll get into in a later post, not in this one. And you might be wondering, well, wait a minute, man, why is the scope at an angle relative to the barrel? I thought they're supposed to be parallel, the scope resting on top of the rifle parallel to the barrel. That's why I say the lens assembly inside the scope. Let's just accept for the moment that this angled relationship is the way it actually is. There is a narrow, thin black line coming out of the barrel labeled the line of departure. That is the line, that is the path the bullet would take after it departs from the bore of the barrel if the rifle were, let's say, in intergalactic space. If the force of gravity here on Earth were not acting on the bullet would just head out in a straight line indefinitely. Look at the dark black line coming out of the scope. headed to the target. That's called the line of sight. We look through the scope with the scope aimed at the target, and we sight through the scope to the target. So that's our line of sight. And notice that the line of departure and the line of sight are different. That is because as the bullet travels toward the target in an upward trajectory, initially along the line of departure, the force of gravity immediately starts pulling it downward away from the line of departure. And if we have our scope zeroed correctly, and I'll go ahead and mention it now, for a particular distance, and we'll talk about that later. But if we have everything adjusted correctly, the bullet will be pulled down by gravity in such a way that it will exactly hit the target where we want it to. And you can see on the right side of the diagram, below the line of departure, I have labeled the actual drop of the bullet from the line of departure to the target. That is the drop caused by the force of gravity. Remember, if we release something, it drops. The force of gravity pulls it down. So the bullet has been pulled down by the force of gravity from the line of departure to the target. Now we're going to take our first look at a ballistics chart or ballistics table, and in future posts we will look at them more. They can be a little bit intimidating at first until you get used to them. Anyway, for the moment we're only going to look at two pieces of data. Well, we'll look actually at three because we're going to look at the top. This is a chart for a .223 caliber cartridge shooting a 55 grain bullet. This is the cartridge, or one of the cartridges commonly shot in an AR-15. Now look on the left side of the chart where it says range. We're going to go all the way down to 200 yards. Let's pretend we're shooting at a target 200 yards away. Now follow that row all the way over to the right under time, and we see that it takes 219 milliseconds for a bullet to travel from that cartridge to travel the 200 yards. Instead of saying 219 milliseconds, because the formula we looked at earlier with T in it has T in seconds, we're going to call that 0.219 seconds. 219 one-thousandths of a second, because a millisecond is a thousandth of a second. So a bullet coming out of a .223 cartridge shot by an AR-15, a 55 grain bullet, will take 0.219 seconds to travel 200 yards. And we're about to use that now. Okay, so from the chart we see it's going to take that bullet to travel the 200 yards, 0.219 seconds. So how far will that bullet drop as it travels out 200 yards to the target? That's what we want to know. We're going to use our formula, D equals 16t squared. In this case, for t, time in seconds, we substitute 0.219. 0.219 squared is 0.048. So the bullet drops 0.767 feet. Remember, in this formula, D is in feet. Well, let's convert that to inches by multiplying it by 12. We have 0.767 foot. That's 767 one-thousandths of a foot. So we multiply that by 12 for 12 inches, and we find out that that bullet's going to drop 9.2 inches during its 200 yards of flight. That calculation gives us a useful and interesting piece of information. It means that if we aimed the rifle without a scope, without even using any adjustable sights. If we simply looked down the barrel of the gun to aim it, if we were shooting at a target 200 yards downrange, we could aim at a point 9.2 inches above our desired point of impact on the target, and when we pull the trigger, the bullet would leave the bore of the barrel, headed initially in the direction of that red point of aim, but as soon as it left the barrel, gravity would begin pulling it downward, and during that 200-yard flight to the target, as we have calculated, it would be pulled down 9.2 inches, and as a result, we would hit our desired point of impact right on target. We'll stop here for the moment. I hope maybe a few of you found that to be at least mildly interesting. It's fundamental ballistic information and theory that we will put to use later as I talk in future posts about how we're going to actually zero a scope, get a rifle, sight it in, and make use of ballistics charts. So thank you for watching.